Hi friends, today we look up at some very interesting phenomena in light called diffraction or bending of light. But before we get into any phenomena, let's look up some things that you are very familiar with and you often ask yourself why this happens. What's the reason? For example, you are all familiar with diamonds and you may have always wondered why diamonds sparkle. Or you may have seen a prism and seen white light entering the prism and breaking into a rainbow of colors and asked yourself why. Or you may try this at home, or you may have tried it already. If you put a pencil in a glass or beaker half filled with water, you'll see the pencil bending and you may ask yourself why. Now the answer to all these lies in the bending of light. The question is, why does light bend? And the analogy is something similar to you are trying to walk through a ground and then you come across muddy waters. Let's say 1 foot is on the ground and another one is in the muddy waters. What happens? You may turn and bend, right? You'll be forced to do so. So that's exactly what's happening here. Light rays come through one medium, tries to go into another, but if the other medium is much denser compared to the first medium, the light will be forced to bend. Now here we are talking about air and diamond is very dense. So this density or the refractive index, where it's coming from? Essentially it is coming from the speed at which light moves through the medium. And if the medium is very dense, the speed is going to be really slow. So the refractive index is given by C divided by V, where C is the velocity of light in air, which is 3 into 10 to the power times 8 meters per second, and V is the velocity in that medium. If the velocity of light through that medium it's slow when the medium is very dense, then this value of V, if it will be less than C when the velocity of light through the medium slows down, then the value of N is going to be greater than 1. In the case of diamond, it is something like 2.42. Now let's closely observe this. You can clearly see that this is the angle of incidence, or this is the angle of incidence, this is the incident ray, and this is the refractive ray. Now if you see these two medium, the interface of the medium is this, right, the dotted line. And if you draw a normal perpendicular to this interface, it's the normal, then the angle that the incident light makes with the normal is much higher compared to the refracted light, as you can see here. But if you decrease the density of that medium, if the refractive index becomes lower, in other words, light moves faster through the medium, then you see the angle of refraction is moving away from the normal. You make the refractive index even lower, moves further away. lower even further away, water further away. And if it's air, it's just a straight line. There's no deviation, no bending. Now, if you know the refractive index of the second medium, and if you know the angle of incidence of the first medium, and if you know the refractive index of the first medium, let's say air refractive index is 1, you know the angle of incidence is 40 degrees, this angle is 40 degrees, and you know that N2 is for diamond is 2.42, then you can find out the angle of refraction, which is theta 2 here. Now, these are the different refractive index for different media, and you can see from ethanol to glycerine to quartz to glass, ground glass, flint glass, sapphire, diamond, rutile, it's all going up, right? Now, another interesting thing to understand, when light is moving from denser medium to a rarer medium, then what happens? For example, if instead of going from air to diamond, I make it goes from diamond to air, what happens? Below a certain angle, say 10 degrees the angle of incidence, then it moves into air. 24.8 is the angle of refraction. But see here that above a certain angle, and I'm increasing the angle of incidence, right? 19 degrees, 23 degrees, and you see around 25, 23, right? 23, and you can make it little bit more, maybe 24. It's almost coming closer to 90 degrees. 25. So the point is that, and let's say if I make instead of diamond this one water, then what happens? Then I can increase this angle little bit further, right? Angle of incidence, and it's still going to the air. Now let's increase it more, and there you go. So for 48 degrees angle of incidence, it is 81.3. If you increase it a little further, then at some point, let's say even you just go to 49 degrees. Yeah, so 49 degrees, you have total internal reflection. No light passes to the air anymore from water. You have total internal reflection. That means light coming from water goes back into water. And this is around 49 degrees, right? The critical angle. And instead of water, if it is diamond, then it is much lower. And I can show you that, yeah, it's around 24, 25. So instead of 49, 24 degrees for diamond, you have total internal reflection. And that's the reason why, now let's come to this phenomenon. It's the reason why in case of a diamond, you have light coming in, gets reflected inside the diamond, and it keeps reflecting, then comes out. But the multiple reflections within diamond is the reason why diamond sparkles. And the reason why these multiple reflections happen, because the critical angle, the angle at which theta, the theta refracted becomes 90 degrees. You just look at this image. you have a ray of light, and then you have the incident ray, and you have the diffracted ray. What light is going from water to air. So always remember that this critical angle business, or the total internal reflection, happens only when you are going from a denser to a rarer medium, never the opposite way, never the other way around. It never happens when you are going from a rarer to a denser medium. Only when you are going from diamond to air or water to air, denser to a rarer medium, then at certain value of the angle of diffraction becomes 90 degree, or it grazes this interface, right? So that's why it's called grazing angle. And so this critical angle is the angle beyond which light simply doesn't get into the other side of other medium at all. It just does total internal reflection, and it has wide applications. I tell you a solution. See this one, optical fiber cable. Light, it goes just like that, and miles light is moving. A signal is moving. How? Because there's a cladding which has a lower refractive index, and light moving from a higher refractive index to a lower refractive index, and does multiple total internal reflections, and it keep moving. So that's how communication systems work globally. That's how important this phenomena is. Or now so now we know that how do we get the incident angle, refractive angle, using this equation which is called Snell's law. And n1, which is the first medium, n2 is the second medium, theta 1 is the angle of incidence, theta 2 is the angle of refraction, and so on, right? Now an interesting problem or interesting phenomena that you may have seen is a white light entering a prism but breaking into different colors. Why so? Why the red color is on the top? And the reason is that each ray of light has a different refractive index. It has a different speed at which it flows through this prism medium. And red light has a higher wavelength. Red is around 700 nanometer. Blue is around 400 nanometers. So this red light, which has a higher wavelength, is interacting least, or is affected least by the prism, the material of the prism, and therefore it has a higher speed and therefore lower refractive index. And from the Snell's law, we know that if the refractive index is lower, the angle of refraction is going to be higher. And therefore, here the angle of refraction being higher, red light is normal, is the angle of incidence. The angle of refraction higher, red light is on the top, and blue light is on the bottom, because blue light has lower refractive index, has higher refractive index, that means lower speed of light. It interacts more with the medium. It has shorter wavelength, 400 nanometer, so interacts more with the medium. What's the analogy? You have a big rope, it doesn't matter so much, but you have a small rope, it will interact with the medium too much, right? So that's basically happening. Big rope and small rope analogy. And therefore interacts with the medium too much, velocity is lower, higher refractive index, therefore angle of diffraction is smaller, and therefore you see the light breaking up in this way. It's also called dispersion. So Snell's law and dispersion all come into effect here. And then the phenomena that you see, a pencil dipped in water, partially dipped in water. Why do you see this bending? And the bending is happening, again, this is Snell's law at play, that if you see the light coming from here, this light passes through water, but then it the angle of refraction is more than the angle of incidence, because water denser medium. And just let's see, if you have light going from water to air, look, the angle of incidence, the light coming in, it's a small angle of incidence, but going out with a larger angle of refraction. And same thing here, that light goes out with a larger angle of refraction. But if you join these lines, if you trace back these lines, you'll see that the image point has shifted. So the apparent image that you see here is basically coming, looks like it is slightly up, and there's a bending, and the reason is basically the refraction of light. So I hope you all like this video. There are several practice problems that you can try. I'll take another class to go through these practice problems. And the link of this video, link to this video, the link from where I am going through from Learn Code Quiz, is provided in the video itself, the description of the video. And do subscribe to this channel. If you subscribe to this channel, you'll get a lot of enthusiasm and support. And have a nice day, guys. Thank you. Bye.